let us start talking about application problem of the second order partial derivative rule. So the problem you are seeing on the screen is reading as identify the extrema of the function by recognizing its given form or its form after completing the square. So at this point, we're just going to look at the function and approach algebraically and understand the nature of the extremums. So let's write down the function. I will start with x squared plus y squared plus 16x minus 8y plus 8, and that is equal to x squared. You write down all the x terms together and the y terms together, so y squared minus 8y plus 8. Because it is 16x, I will go ahead and write 2 times 8 times x in order to have the triplet of completion of square. And this new multiplier is 8, so I will say 8 squared. Similarly, I will do y squared minus 2 times 4 times y, so I will say plus 4 squared because my new multiplier is 4. I had plus 8 to start with. Now I added 8 squared, so I subtract 8 squared. I added 4 squared, so I subtract 4 squared to balance my relation. So I get, remember the first 3 terms altogether is the triplet for the completion of the square, and I go ahead and call this thing x plus 8 whole to the power 2. And similarly, I'm going to go ahead and say that y squared minus 2 times 4 times y plus 4 squared is plus y minus 4 whole to the power 2. And finally, I have 8. 8 squared is 64. 4 squared is 16. So that simplifies to x plus 8 whole to the power 2 plus y minus 4 whole to the power 2. Minus 64 minus 16 is minus 80 plus 8 is minus 72. Now think about this shape. While this represents a circular region of radius square root of 72 units and centered at negative 8, 4. So I'm going to try to draw this and understand the extremum from there. So as I said, think about the Cartesian coordinate system. I might have to make it a little bigger, but we'll start with this, and I have the center at negative 8. So let's go ahead, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. And the y coordinate is 4, so I go to 1, 2, 3, 4. So my center of the circular region is here, and I'm thinking of a circle of radius square root of 72 units. And the reason I'm saying this thing, if you instead of doing all this work had set everything is equal to 0 in order to understand the relation as an equation, then you would end up having 72 on the right hand side, which is a square root of 72 whole to the power 2, which satisfies the equation of a circle. So now I'm thinking of a circle, say of this format. So see what happens with this circular region. It is going to help you understand whether there is any maximum or minimum for this function. So the way we are going to understand this maximum minimality is changing our equality to an inequality. So if it is equal, I get a circle. But I am trying to talk about the maximality and minimality in terms of understanding the extremum. So change equality by inequality. So I'm going to say my relationship was x plus 8 whole to the power 2 plus y minus 4 whole square minus 72. Now I'm getting back to the relationship. Now think about x plus 8 whole square. X plus 8 whole square, the minimum possible value of this thing is 0 because this is the perfect square term. Similarly, y minus 4 whole square, the minimum possible value is also 0, cannot be any lower than 0. So what is the minimum possible value for your function? So I will go ahead and say minimum possible value for this given relationship, possible value for the relationship is the minimum possible value for x plus 8 whole squared, which is 0, plus minimum possible value for y minus 4 whole squared, which is 0, minus 72, and that is equal to negative 72. And where it happens? It happens when x plus 8 whole squared is equal to 0, and when y minus 4 whole square is equal to 0, which implies what? X equal to negative 8, y equal to 4. So I get to say negative 8 for x, 4 for y, negative 72 for z is the minimum. How about the maximum? So what I have done, as I was referring to, changing your equality to inequality to find the minimum, I wanted to say the given expression must be greater than or equal to a value. And I wanted to know what value it must be greater than or equal to. To find the maximum possibility, I would do the other way around. I would say, is there any option such that these values are always less than or equal to? So I will go ahead and say, what is the possible value? So the relation x plus 8 whole square plus y minus 4 whole square minus 72 is always less equal to this value. Is there any value like that? Let's try to understand this answer. I will say there is none. How come there is no such value? As x goes to infinity, y goes to infinity, x plus 8 whole square goes to infinity, y minus 4 whole square goes to infinity. Hence, even if I subtract 72 from infinity, I still end up having infinity. X plus 8 whole square plus y minus 4 whole square minus 72 all together will go to infinity. So there is no such value where the function is going to be less than or equal to the given values. I cannot find one such value for which I will have my function less than or equal to that given value. So no maximum. So what I'm going to do now, I'm going to go back to the problem and read the rest of the problem. We are done with the first part of the problem, but the problem is now telling me verify your results by using the partial derivative to locate any critical point and test for relative extrema. So now the results I have obtained, so I already obtained that the relative minimum, there is something. I'm going to go ahead and say that the relative minimum is happening at negative 8, 4, negative 72. But relative maximum, I have to say, does not exist, and I'm going to verify that using the second derivative test. So I will go and open a new page for myself and start working on this thing. So to start with, again, I'm going to just go ahead and write down my function. So my f of xy, it's a function of two variables, is equal to x squared plus y squared minus 16x plus 16x minus 8y, and let me was plus 8. So now I'm going to start taking the derivative. So f of x, derivative with respect to x, is going to be 2x plus 8. Remember the second derivative process? You set this term equal to 0, solve for x. So you get 2x equal to negative 8. I'm so sorry. So we should have had 2x plus 16. And then I would set it equal to 0. So 2x is equal to negative 16. Solve for x, x is equal to negative 8. Now I do fy. Fy is the derivative with respect to y, and I get 2 times y minus 8y equal to 0, which will solve for the value of y. Again, I said 8y, it should be just 8. So 2y is equal to 8. Solving for y will give me 4. So the critical point, I found only one of them, and that is given by negative 8 comma 4. I'm going to use that information and try to solve using D-Alembert. So D, if I remind you the term, is fxx times fyy minus fxy whole to the power 2. And all of these terms will be evaluated at this critical point. So let's try to find out what is fxx. Fxx is the derivative of fx, and when I do the derivative with respect to x, I get 2. Fyy is equal to, well, do the derivative of fy and you get 2. So I actually do not have to evaluate, or so to say, if I do fxx at the critical point, negative 8 comma 4, I still get 2. 2 is a constant function, so it doesn't change anything. Or in other words, fyy similarly at negative 8 comma 4 is still 2. And I'm going to find fxy. Remember, fxy is finding the derivative of fy with respect to x. So this is fy. I do the derivative with respect to x, I get 0, still a constant function. So I get to say fxy at negative 8 comma 4 is equal to 0. I come back, put these values in my D-Alembert, and I will get D equal to 2 times 2 minus 0 squared, which is 4. Remember, that's greater than 0. Tells me, check the sign of fxx. Well, fxx is equal to 2, which is also greater than 0, which tells me negative 8 comma 4 refers to the local minimum. Relative minimum. That's just the rule, relative minimum. And how do I end this problem? Well, I have to find the point of the relative minimum. So I'm going to input negative 8 and 4 in my original equation. So I will say f at negative 8 comma 4 is going to be negative 8 to the power 2. That's my x squared plus y squared, so 4 squared, plus 16x, so 16 times negative 8, minus 8y, so minus 8 times 4, and then finally plus 8. So let's see how much we get. I get positive 64 plus 16, and I get negative 128 minus 32 plus 8. So 64 plus 16 is 80, plus 8 is 88. Negative 128 plus 88 is negative 40. I have one more negative number. Together they give me negative 72. So I say the point of local minimum in this problem is given by negative 8 comma 4 comma negative 72. And if you remember, that was exactly what we have obtained from our work just doing the algebraic manipulation of completing square. And since there is only one critical point, I will also go ahead and say that there is no point of local max or relative maximum. And that answers my question.